Yes, we're still.
So have you guys started with your homework? Because I think the deadline is coming soon. Yeah, I know some people haven't started. That's why I say started. So let's look at let's look at the proton NMR spectrum of allyl bromide. Okay. Let's try to see if we can understand this proton NMR spectrum. So from the structure of allyl bromide, we'll probably have 4 different sets of peaks. We'll have 4 different sets of peaks. Those peaks are labeled A, B, C, and D. Okay? Now, our task is to be able to determine which peak is what. Okay? Which peak corresponds to what? A, B, C, and D. In this case. Now, first thing I want you to take note is, I need you guys to understand why C is different from B. Okay, that's the first thing I want you guys to know. That proton C and proton B are different. And this is simply because they don't have the same chemical environment. Okay, if I look at the molecule across that line, that plane of symmetry, I notice that B is in the same phase with D, whereas C is in the same phase with A. So you see the chemical environments are not the same. So that's what distinguishes C and D. So that's why we'll have a different signal for C and a different signal for D. Does that make sense?
Yeah.
Thanks. Okay. Okay, now based on the integration is represented by the red line. Okay, the sum of the integration is equal to the number of protons in the system. So we are good with that. Sum of integration is equal to the number of protons in the system. And so here with an integration of 2, that will correspond to hydrogen sets A. Now we have the remaining hydrogens that we need to be able to give the integration. We have the remaining hydrogen that we need to be able to determine the integration. Okay, and over here we'll have integration of hydrogen B, hydrogen C, and hydrogen D. Question? Yes.
Did you place C in front of B because technically C is closer to the VR than B?
Yes, I can put it that way. Yes. Question, Jakira.
Wouldn't A be more distributed because it never has the VR? Yeah, next to the VR. That don't make sense.
Do not forget. Remember, we have that double bond in there. Remember, if we go back like a couple of slides up, there is that general table that I gave you guys in the past. The table I said you guys need to know. Okay? This table, you remember this table? You see this table? When you are connected to a BR or an electronegative group, your chemical shape is between 2.5 and 4.5. So when the proton is connected directly to a double bond, the chemical shape is between 4.5 and 6.5. And we explained that already when we looked at the anisotropy. You remember those electron current and all the rest. Okay, that was explained. We explained it using this, the electron current. Okay, and so if we go back, that's why B is where it is. Where are we? Here. So that's why B. Oops. That's why A is between 2.5 and 4.5, remember, okay, connected to the bromine. And then the ones on the double bond are between 4.5 and 6.5. Does that make sense? So that table is important for you guys to have it as a picture in mind, to know about where groups of protons will appear. Another question? Yes. Well, we explained that B is closer to the bromine than C, and we'll talk about why. Okay, I will let you know. We'll have a special name for that. I need another question. Yes, sir.
I understand how A is the one right there because of the integral, but how do you differentiate between C and B and D? Because like it kind of looks like D is the closest out of all of those to the VR.
That's a good question. Yeah, that's a good question. We'll answer it. We'll answer it. Now, look at the multiplicity. Look at their multiplicity. Is that okay? If you look at proton D, how many neighbors does it have? Like how many neighbors does D have? Okay. D will have A as neighbor. That's a normal neighbor, 3 bonds away. Do you see that? Okay. Now, let's pay more attention. Look at D and A. They are 3 bonds away, and all those 3 bonds are single bonds. Does that make sense? So those are 2 hydrogens. So normally we expect to see a normal triplet. Is that okay? Because you are 3 bonds away, that gives you n plus 1. If you have 2 hydrogen, the n plus 1 rule say you should be a triplet. Does that make sense? So normally we expect D to be a triplet. But then D is also what? 3 bonds away from C and B. Do you see that? But the types of 3 bonds away between B and C is not the same as the type of 3 bonds away between B and A. Do you see that? B and C, we have a double bond in between. Now, I'm speaking Chinese now, or Homala, right? I think I'm speaking my native language. Nobody is getting me. Let's look at the distance between B and C. Look, you have 1, 2, 3. 3 bonds. But among the 3 bonds, you have a double bond there. Do you see that? You have a double bond there. But then if you want to compare B and A, D and A, instead of drawing that hydrogen, I will draw the hydrogen out here. If you compare D and A, you have 1, 2, 3 bonds also. They are all 3 bonds, but the problem is that between B and C, you have a double bond in there. And between B and A, there is no double bond. So technically, the distances between B and C is not the same as the distance between B and A. Does it make sense now? Between the single bond and the double bond, which one is longer? Single bonds are longer. Okay, so you expect the distance between D and A to be longer. Is that okay? Because it's made up of 3 single bonds. So you expect that distance to be longer compared to the distance between B and C. B and C is made up of 2 single bonds and 1 double bond. Is that okay? Now, because those distances are different, they are all neighboring D, but they are not the same type of neighbors. Does that make sense? You have a neighbor that lives just 1 house away from you, and you have another one that lives a couple of streets away from you. We are all neighbors, but not the same. The relationship we will share together will not be the same. Does that make sense? Is that okay, guys? Yeah. The relationship will not be the same. So, D will first see A as a normal neighbor. Then we'll see C as another type of neighbor. So, it will further split that triplet. And it will also see B as another type of neighbor. And it will further split that funny splitting pattern that we had already. Does that make sense? And that's why you have a bunch of stuff there in D. Is that okay? You see this bunch of signal here in D because D has a normal neighbor and two in quote abnormal neighbors. That comes over and then keeps splitting that relationship. Yes.
So, I mean, I have like 6 million students. I mean, we should like 6 million. Does the double bond like double the amount of like registers you count? So it'd be like 2 for B, 2 for like, I forgot that word. C? That's a C, right? So B and C would have like, you would count it as 2, and then you just count the 2 hydrogens on A, which would be 6.
It's more than 6 in there. It's more than 6 in there. So, if B couples with A, okay, if B couples with A, you will have a normal triplet. Does that make sense? When B couples with A, that gives you a normal triplet. If B couples with C, that triplet will further be split by C, okay? So this triplet will be split into a doublet, that small triplet. This also will be split to another doublet, this will be split to another doublet. Does that make sense? And then it will further be split by B. So these doublets again will be further be split. Does that make sense? So that's why it keeps giving you that bunch of peaks. It gives you that bunch of peaks. Okay. Now, this is where we now make a difference. There is a difference between what we call a quartet and there's a difference between what we call a doublet of doublet. Okay, there's a difference between a quartet and there's a difference between a doublet of doublet. A doublet of doublet is simply 2 doublets that are very close to each other. Compared to a quartet, you can see the quartet is having a pyramidal shape. Quartet is having a pyramidal shape, whereas a doublet of doublets, they all have the same shape. Okay. Now, let's look at another NMR spectrum before we get into something else. Let's talk about ethyl benzene. Ethyl benzene will be an NMR spectrum with 5 different signals. Okay, it will have a total of 5 different signals. This will be proton A and that will be proton B. The multiplicity of proton A will be a triplet, that of proton B will be a quartet. That is easy, right? Now, when you come here, this proton 5 here, or this 5 here, actually represent all the 5 protons you have on the benzene ring. Okay? So if you look at your benzene ring over here, it's taking time to load, I don't know. If you look at the benzene ring here, you understand why proton C are the same, because they are all auto to the ethyl group. This is the ethyl group. That's the ethyl group. They are all auto to the ethyl group, so they will have the same chemical shift, same chemical environment. And then proton D are meta. Are meta to the ethyl group, and proton E is in the para position. Okay, those are all different set of protons. So you have 3 different set of protons. Now, proton C will only have 1 neighbor, which is D. Does that make sense? C will have 1 neighbor, which is D. And so you expect C to give you a doublet. D will have 2 neighbors, E and C. Does that make sense? So the multiplicity of D will be a triplet. And E will also have 2 neighbors. Those 2 Ds. So E should also give us a triplet. Does that make sense? So the bunch of signals you see over here is actually a set of 3 signals. A doublet, a triplet, and a triplet. But because the chemical shape are very close to each other, they kind of, junk or packed up in a very narrow range. Is that okay, guys? So the signal for Hc, Hg, and He proton overlap with each other simply because the chemical ship are very close to each other. Does that make sense? Is that okay? Chemical ship are very close to each other. But then if we have nitrobenzene can actually spread those chemical shift away. If you have nitrobenzene, that will be C. If this is A, then that will be A, and this one will be B. That will be B. Okay? So these two here will give us a doublet. You will have a signal, a doublet, and you can see the doublet here. You can clearly see the doublet there. Does that make sense? This doublet here, around 8.3. That's the doublet. And that doublet is because of the protons in the ortho position of the nitro group. Okay? Then you will have B. B will appear as a triplet because it has two levels. And that's the triplet over here. 1, 2, 3. You can see the triplet over there. Does that make sense? Which one? A. This is A. What do we expect A to be? The triplet, right? And that's the triplet.
You said that first two set, when you kind of like do the connection, that is the ortho position, you said?
That's the ortho position.
Okay.
Yes. So that's the ortho position, the meta and the para, okay? Ortho, meta, and para. Question, guys, please, I need a question. Remember, the way we label it alphabetical order, okay? A represents the shielded proton, and Z, A, B, C up to Z, you know, as we go up, it represents the shielded proton. So I need a question from you before I move. I need a question, guys. Why do we label it A, B, C the way it is? Since you guys don't want to ask me the question, let me ask it. Okay. Why is C labeled C? Not, C is there. You have C, you have A, you have B. B seems to be further away. B seems to be further away from the nitro group, right? And if B was further away from the nitro group, then you should expect B to be the most shielded. Does that make sense? If you look at it logically, we say the further away you are from an electronegative group, the more shielded you are. And so B is far away from the nitro. So expect B to be the most shielded. So expect this to be B. Which one? This to be B, but that's not the case. Why is B the shielded compared to A? Why is A shielded? Does that make sense? Why is A shielded? That's the question. Now we've labeled this position, the ortho, the meta, and the para position. In an aromatic ring like the one we have here, those positions behave differently. Some of them are electron-rich positions, some of them are electron-poor positions. Does that make sense? Okay. And usually, the meta position, which is where A is, are usually electron-rich positions. When you have that nitro group over there. When we have that nitro group over there, so they'll technically be a shielded position in the presence of the nitro group. And the other positions will be electron deficient, so they'll be the shielded position. That's why they will appear with a high chemical shift. Does that make sense? Early in the morning. Next property of an NMR spectrum, we've talked about the integration, we've talked about the chemical shift, we've talked about multiplicity, now we're talking about the coupling constant, J. The coupling constant is simply the distance between adjacent peak, okay? The distance between nuclei. Remember when we're talking about the ethyl bromide, we're talking about this one. I was talking about the distance between Z and A and D and C. That distance is what we refer to as the coupling constant. So in other words, I would say instead of saying the distances are different, I would say they have different coupling constant. Does that make sense? That's basically what the coupling constant is. Now, protons that coupled together have the same coupling constant. Meaning if A couples with B and B couples with A, so they will have the same coupling constant. And that coupling constant is referred using the letter J. So J stands for the coupling constant. So if, for example, with this molecule here, chloroethane, A couples with B would be the same distance as if B was coupling to A. So that's what we call JAB equals JBA. I will only stop here. This is for your information. I won't continue too much with that one. But what is important with coupling constant, usually to distinguish between cis and trans isomers. Coupling constants are good in doing that. Yes?
Where do you actually see the coupling constant on the NMR?
It's a distance that separates the peak. So if you measure that distance between two peaks, that's what we refer to as a coupling constant. That information is really necessary when you want to do a stereochemistry study. Distinguish between a cis and a trans isomer. For example, if you look at this one here, in the first structure, the protons are trans to each other. And when they are trans to each other, they are far away from each other. Does that make sense? Compared to when they are cis. So when they are trans, they are far from each other. That's why the coupling constant is 15 Hertz. Compared to when the protons are cis to each other, the coupling constant is 10 Hertz. Cis, they are closer to each other, 10 Hertz. Trans, they are far away from each other, 15 Hertz. Does that make sense? And I come back again, because I come back again to this one. You remember, some of you told me that C, initially, some of you told me that C is closer to the Br compared to, C is closer to bromine compared to B. Does that make sense? Because C is cis to that group, so they should be closer to each other compared to the bromine, which is trans. Remember, the cis has a lower coupling constant than the trans. Is that okay? And that coupling constant is basically the distance. You guys should read the summary. That's the summary. Yes.
Can you show that calculated showing where you had an arrow B, B, and C, and you're showing us the so you're saying that if it's cis, it would be closer to each other. So then, why would it be next to B if the distance to be closer to each other?
No, we're more interested in that bromine because that's the electronegative group somehow. That's the electronegative group. So remember, the distance, the further away you are from the electronegative group, the less deshielded you are, or the more shielded. Does that make sense? So that's why we're looking at that electronegative group as a reference. So if we summarize all what we've learned here in proton NMR, the number of signals tells us the set of equivalent protons in the compound. So if you count the number of signals, that tells you the different types of proton. The value of the chemical shift gives you information about the chemical environment of those protons. Do you have alkyl, benzyl, or alkene, or allylic? You know, that's what the chemical shift will tell you. The integration gives you information about the number of protons responsible for that signal. That's what integration is. The splitting pattern or the multiplicity gives you information about the neighboring protons. How many neighbors you have. N+1 rule. That's what we call the splitting pattern, multiplicity. And then we now talk also about the coupling constant that identify protons are coupled with each other. Like I said, coupling constant is very, very useful when you want to distinguish between cis and trans isomers. And so, for example, in this case, we have a cis and trans isomer here that we need to distinguish between them. Okay, trans 3-chloropropanic acid and the cis counterpart can easily be distinguished using NMR. Okay, if you measure the distance between the peak, that's the distance we're talking about, that distance there between two peaks. If you measure that distance between the peak in the trans isomer, the distance will be about 14 hertz. But if you measure that same distance between the peaks in the cis isomer, that distance will be about 9 hertz. Okay, 9 is closer to 10, 14 is closer to 15. So the one with 15 will most likely be the trans isomer, the one with 9 will most likely be the cis isomer. Okay, that's how useful coupling constant can be. We'll not talk more about coupling constant. If you want to read more about coupling constant, you have tons of slides that I have crossed out. That's for those who want to read more about coupling constant. Okay, let's see if we can do something that will distract us a little bit from all this. Let's distract ourselves from all this. Should we do problem 27 or not 28? Huh? We should not do it or what? Let's do it. Let's do problem 28 from your textbook. I didn't have time to prepare that as a question you guys can easily click. Describe the proton NMR spectrum you will expect for each of the following compound. Indicate the relative position of the signals. So, A, let's describe what the NMR signal, the proton NMR for A will look like. It's a description. So when we talk of a description, I expect you guys to tell me how many signals will the proton NMR have, what will be the integration of those signals, okay, what is the multiplicity, the splitting pattern of those signals. Then you can now label those proton A, B, C, D, based on A being the most shielded one and then Z being the most deshielded one. Okay, so let's describe it. And the best way to describe stuff is also by drawing. Okay, drawing can be a nice way to describe things. So let's describe the NMR of A. How many signal are we expecting to have in the proton NMR of A? 2 signals, right? We have a set of 2 signals in the proton NMR of A. So these are proton A and those are proton B. Does that make sense? So we expect to have 2 signals. And so proton A will show a triplet. Okay. So proton A will give us a triplet, and that's clear because we only have 2 neurons. And what about proton B? Proton B will also give us a triplet. That will be the set of B. Does that make sense? Yes. Oh, they only have 1 neighbor, which is B. Does that make sense? A only has 1 neighbor, which is B. That's why it's a triplet. And B only has 1 neighbor, which is A. Is that okay, guys? So that's how the NMR will be. And so you can define the integral. The integral of A and the integral of B. A will have an integral of 2. B will also have an integral of 2. Or you can all say they will have an integral of 1, 1. Or they can have an integral of 4, 4 if you want to. Does that make sense? So they will have the same integral. They will have the same integral. Yes.
Okay, so
If you have one neighbor, n plus 1, then you have a doublet. But if you look at A, this is A. This is the only neighbor of A, B. So 2 hydrogens, 2 plus 1, 3. That's why you have a triplet. Does that make sense, guys? Let's do B. Let's describe the proton NMR for B. Let's describe the proton NMR for B. So with B, how many peaks, how many signal do we expect in structure B? Yes, we expect that much. 4. Okay, so we need to give those signals. We need to label them. Okay, so I will label this one A. Remember, A stands for the most shielded one. Does that make sense for everyone? Why that guy is A? Is that okay? That's A. So, this is next to bromine, which is an electronegative group. This is next to an oxygen. This is next to an oxygen. This is the only guy who is not kind of close to an electronegative group. So he will most likely be the most shielded one. Does that make sense? Now, this CH2 is closer to bromine. This CH2 is closer to oxygen. The CH3 is closer to oxygen. The question is, between bromine and oxygen, which one is more electronegative? Oxygen. It means that the one closer to bromine will be shielded. Does that make sense? The one closer to bromine will be shielded because oxygen is more electronegative. And so this is most likely our B. Does that make sense, guys? Yeah. Okay. Now we need to distinguish C between the CH3 and the CH2. Which one will be C? CH3. You remember when we talked about it in class here? When we talked about the methyl, the methyl, and the methylene protons. Okay? So in this case, that would be my C, and that would be my D. Does that make sense? Okay. Now, the next one is what is it? Multiplicity. In terms of multiplicity, B. What would be the multiplicity for B? B would be a triplet. Okay. Multiplicity for A. That will be 5. Is that okay? Because A has 4 neighbors, 2 on either side. Okay, so that will be 5. It will be a quintet. I will write it as a capital Q or a multiplet if you want to. What about D? D will be a triplet. Does that make sense? And what about C? C will be a singlet. Does that make sense? C will no neighbor. C doesn't have any neighbor. Some of you guys are just looking at me as if I'm a mirror. A quintet. Well, usually, 5 and above or 6 and above, if you call it a multiplet, that's fine.
You said it has 4 neighbors.
You have 2 here and you have 2 there. Yes. A triplet. Because this is the only neighbor of D. No, the CH3, if you look, it's more than 3 bonds away. Okay, the CH3 is more than 3 bonds away. Okay. 1, 2, 3, 4. Do you see that? With the CH3 is more than 3 bonds away, that's why it's not a neighbor. And that's also why the CH3 will be a singlet. Does that make sense? That's why the CH3 will also just be a singlet. Because it doesn't have any neighbor. Is that okay, guys? Yeah, when you guys don't understand, I can see that from your faces. You look at me like, I don't know, coming from space. Yeah, it looks like things are not moving. What's happening? Martin Luther King holiday or what? You should instead be motivated with the Martin Luther King holiday. Let's look at C. Let's look at C. So how many set of protons do we have in there? How many set of protons? How many signals are we going to see in the NMR of C? We'll only see one signal. And that signal will be a singlet. It will be a lone guy just standing there like that, looking at you. Does that make sense? C will only give you one signal. Just one. And it will be a singlet. These are the most difficult types of NMR to analyze. Seriously, I'm telling you. When you have this kind of NMR, you know, it's just like one peak. Just one peak standing there. Yes. This is the same as this, which is the same as that, which is the same as that. Does that make sense? Are we good up to this level, guys? Yes.
So you said this is hard to distinguish from the text, so will we ever see NMR?
She's saying on the text. Do I answer those kind of questions, guys? I don't answer questions that says on the test or on the exam. We just saw it, right? Oh, no. It's on January 31st. 31st? It looks like, yes. Until further notice. Until further notice is January 31st. Okay? Until further notice. It's January 31st. So, problem number 28. You guys look. You guys have a bunch of job to do, okay? You have a bunch of job to do. Go and finish it. Finish it. Finish it. You have a whole lot of stuff to do there. What are enantiomers? Okay, non-superimposable mirror images. That's the best definition of what enantiomers are. Non-superimposable mirror images. Now, in NMR, there's a group of protons, we refer to them as enantiotopic protons, enantiotopic hydrogens. Okay? Now, if you replace an enantiotopic hydrogen with something else, for example, deuterium. Deuterium is another form of hydrogen. If you replace it with something else, then you form an asymmetric center. It means that that proton was enantiotopic. Does that make sense? Replacing an enantiotopic hydrogen with any other group, if that creates a chiral center, then that proton was enantiotopic. Does that make sense? So let's look at this guy, for example, this example here. This is ethanol. This is ethanol. CH3, CH2, OH. That's ethanol. How many signals? How many signals are we expecting to have in this spectrum? Forget about this OH, forget about this hydrogen here. We're only focusing on the hydrogen connected to carbon for now. So we expect to see two signals, basically, two signals. But then, proton A and B are described to be enantiotopic. Okay? They are described to be enantiotopic because if you decide to replace, for example, let's replace proton A with another group of hydrogen. Let's call it X. Let's replace it with another group. Instead of replacing it with X, let's replace A with a CH3 group. Oh, not the CH3. Let's replace that with a chlorine. Does that make sense? If you decide to replace A with the chlorine, now this carbon here becomes chiral because it will have 4 different groups surrounding it. That's hypothetically. You are not actually replacing it. But you imagine that, okay, if I replace it with another group, does that carbon become chiral? Yes, the carbon becomes chiral. If you replace B with another group, that carbon also becomes chiral. So A and B are enantiotopic. And when they're enantiotopic, they are chemically equivalent. And you know what it means to be chemically equivalent. What is Samantha? Why? She's not in. Yeah, no, yes. No, Sam, yes, I know. Yeah, I know most of you, so. Does that make sense with enantiotopic protons? Okay? Enantiotopic protons are chemically equivalent. If they're chemically equivalent, it means that they will give you the same signal. That's basically what a chemical equivalent means. They will appear as a set of protons. And so your ability to distinguish which protons are enantiotopic is very important. But then next ones are what we call the prochiral protons. Okay? So those enantiotopic protons are also prochiral. So you know what it means, prochiral? It means that you have the tendency of becoming chiral. And so that tendency, you can either form the S enantiomer or you can either form the R enantiomer. Does that make sense? You have that tendency of either forming the S or the R. The representation we have on the board is a Newman representation. A Fisher representation. That's a Fisher representation we have on the board. And it happens that if you replace HA, proton A, with any other group, chances are that you will form the R enantiomer. That's why it's called pro-R. Does that make sense? If you replace that with a deuterium, D, deuterium is D, it's a form of hydrogen. If you replace that with a deuterium, then you will form the R enantiomer. And if you replace proton B with deuterium, then that will give you the S enantiomer. That's why it's referred to as pro-S enantiomer. Is that okay, guys? And those are all enantiotopic protons. They are all enantiotopic protons. Any question? You remember how to distinguish, how to determine the R and S configuration from a Fisher projection. You remember that, right? Yeah. So if you don't remember, let's recall it. So imagine we have that same structure here. And here I have a deuterium, I have an OH, and I have HB. Priority number 1 is the oxygen. Priority number 2 is the carbon. Priority number 3 will be deuterium. And so my clock is moving in that direction. Okay? That's the clockwise direction. And that's the R direction. I maintain the direction because my lowest group is in the back, vertical bond. Does that make sense? The lowest group is in the back, the vertical, so I maintain. If the lowest group wasn't there, then I'll have to reverse. Does that make sense? If the lowest group is on the horizontal, then you reverse. If it is on the vertical, you maintain. Yes?
So an enantiotopic hydrogens are also the pro-R, pro-S.
And in enantiotopic hydrogen, one of them will have a pro-S and one of them will be pro-R. Meaning that if you replace that one with a deuterium, you will most likely form the S enantiomer or the R enantiomer. Does that make sense? Another set of hydrogens are distereotopic. You remember what diastereomers are? Okay? For you to be able to form a diastereomer, you need to have at least 2 chiral centers. Now, with diastereotopic protons, those are protons next to a chiral center. Does that make sense? So you have a chiral center in the molecule, and then you have a set of protons that are standing next to that chiral center. So this is a chiral center here. And we now have this set of protons standing next to that chiral center. So these protons are no longer enantiotopic in this case. They are not enantiotopic because they are standing next to a chiral center. they become distereotopic. Does that make sense? They become distereotopic. And unlike enantiotopic, where we have the same chemical environment, with distereotopic protons, we will have different chemical environment. Does that make sense? Enantiotopic gives you the same chemical environment, meaning the same signal. The distereotopic proton gives you different signals. So in a distereotopic element, HA and HB will give you different signals. They will look at each other as neighbors, not brothers. They will be neighbors. Brothers will live in the same house. Neighbors will live in different houses, unless the parents travel and then they decide to send their kid to stay with you for the weekend. Yes, sir. Does that make sense? Okay. And so that's the difference between enantiotopic hydrogen and distereotopic protons. Because if you now replace one with a deuterium, you will now form two chiral center. One of them will be R, the other one will be S, and you can also form the RR and the RS and blah 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 blah. You form a set of diastereomers. Okay, you form diastereomers. So just like we said, those diastereotopic protons are not chemically equivalent. It simply means that they will give you different NMR spectrum. They will give you different NMR spectrum. Okay. Now, the rate of replacing those protons to form the E enantiomer, which is similar to a trans, is faster. And we can understand why it's faster to form the E enantiomer. Why is it faster to form the E enantiomer? Because it's the more stable. Does that make sense? That's why it's faster for you to form the E enantiomer compared to forming the Z enantiomer. Okay? And you can easily distinguish between the E and the Z enantiomer proton NMR. How will you distinguish between those NMR? What will be the distinguishing feature? The coupling constant. Thank you, sir. Does that make sense? You can easily distinguish between the Z and the E using the coupling constant. The Z is similar to a cis, so the coupling constant will be around 10 Hertz. The coupling constant between this hydrogen and that hydrogen will be about 10 Hertz. Whereas the coupling constant here between this hydrogen and that hydrogen will be about 15 Hertz. That's what will help you distinguish between those two. Okay, I think I will stop about proton then. I want us to look about we'll talk about carbon NMR now. Yeah. The rest of the stuff is for you guys to go ahead and read it. Okay? Read it. I want us to move forward. So we're done with proton NMR spectroscopy. Any question? Any question on proton NMR spectroscopy? We've basically done everything. The rest is just more details for those who want to read. Okay? More details. Carbon 13. Now, in a carbon 13 NMR, the number of signals reflect the number of different kinds of carbon in the compound. That's no news, right? This is no news. It's the same story like in proton NMR. The number of signals tells you the number of protons you have in the type of protons you have in the compound. In the carbon 13, it tells you the types of carbons you have in the compound. Does that make sense? And the type of carbons, you also distinguish them the same way as we do for the proton NMR. Is that okay? So if I give you this example here, CH3, CH2, OH. So how many signals do you expect to see in the carbon NMR for this compound? 2 signals, okay, because there are 2 types of carbon. Does that make sense? You have 2 types of carbon, so you expect to see 2 signals. Okay. Now, if you remember the chemical shift for the proton NMR, remember I told you it ranges between 0. It ranges usually between 0 up to around 14. That's what the chemical shift range for that one is. But for the carbon NMR, the chemical shift can go up to 220 parts per million. So it goes really high. Okay? It goes really high. We also use TMS as a reference for the carbon NMR. We also use TMS as a reference. Now, the position of the signals in the carbon NMR also gives you information about the chemical environment of the carbon. Does that make sense? The position. Another thing, in carbon NMR we don't talk about multiplicity. So multiplicity doesn't exist in the carbon NMR. Does that make sense? So every signal in a carbon NMR will simply be a singlet. Every signal will be a singlet. There is no multiplicity. And this is because normally there's supposed to be multiplicity, but those multiplicity were decoupled. We refer to carbon NMR as a decoupled spectrum, meaning that we decided deliberately to kill those multiplicity because that would be too much information. Yes?
So let's say you had a carbon bond between methyl and ethyl and those bond between oxygen. Wouldn't that technically only give you like 3 signals, but you still have 4 hydrogens?
CH2 here and the CH3. No, that will give you 4 signals. Because we have 4 different types of carbon. Okay, this will give you 4 signals. Does that make sense? This will give you 4 signals because we have 4 different types of carbon. Okay? 4 different types of carbon. Like I said, in terms of multiplicity for carbon, the multiplicity will simply be a singlet. It will simply be a singlet because the carbon NMR spectrum is decoupled. If we don't decouple that, then the multiplicity will be a real mess. I will explain why it will be a mess. If you consider this carbon here, how many neighbors does it have? The carbon underline, this guy here, let me underline it. How many neighbors does that carbon have? Okay. That carbon technically has 4 neighbors. It has the 3 hydrogens plus the other carbon that is bonded to. So it will have these 3 hydrogens and it will also have that carbon. So in terms of multiplicity, that gives you what? 4 plus 1, 5. So this will be like a quintet. If you consider this carbon, how many neighbors does it have? It will have the 5 hydrogens plus the 2 carbons. And you see things are becoming messy. Does that make sense? And so because of that mess, the multiplicity were cancelled in carbon NMR. So we call that decoupled. So all carbon NMR just gives you a single peak, single signal. Does that make sense? And so over here we have a table with an approximate value. Okay, that's a table just for your appreciation. And that table is not very different from what we saw for the proton NMR. They are kind of very similar. Okay, between 0 and 50 chemical shift, you will most likely have sp3 carbon. Okay, you most likely have sp3 carbon. And carbons that are connected to nitrogen, chlorine, bromine, they will appear in the upper range. You know, usually they will appear between 40 and 70. Between 40 and 70, that's where they will appear. Carbons directly connected to those hydrogen. See, it's the same stuff as in the proton NMR, just that it's multiplied by a certain factor. Okay. Then the sp2 carbons, the sp2 appears between 100 and 150. So if I give you a carbon NMR and then you see a bunch of signals between 100 and 150, chances are that those carbons belong to an sp2. Does that make sense? And then carbon double bonded to oxygens, they will usually appear in that upper range. So for example, if I give you a ketone like this carbon here would be around 200. So this is another table that is good for you guys to have it in mind, okay? It's good for you guys to have it in mind. And we interpret the carbon NMR exactly the same way as we interpret the proton NMR. So here we have a carbon NMR of this compound here. That carbon NMR will give us 4 signals. It gives 4 signals because we have 4 different types of carbon. And they are all labeled A, B, C, D. And the labeling is exactly similar to what we've been doing before. Okay? It's exactly the same. We label them exactly the same as what we've been doing before. And if you notice, all of them are singlets. They are all singlet. Because I said it's decoupled. Does that make sense? They are all decoupled. And so we have that for the signal A, and over here for signal B, and over here for signal C, and this other one for signal D. Does that make sense? And D is where it is because D is the one connected to the oxygen. And so the further away you get from oxygen and da. Does that make sense, guys? So it's the same story as the proton NMR. It's the same story as the proton NMR. Nothing really special here. And so here they were trying to explain. I will not talk too much about this one because we've talked about it already. Here they were trying to explain and they said, okay, what if we didn't decouple the carbon NMR? How would that look like? If we didn't decouple that carbon NMR, it will tend to look a little bit like this one. Okay? You'll see it will give us all those multiplicities there. And trust me, it becomes a mess. And so that's why we don't worry about coupled carbon NMR. We only worry about decoupled carbon NMR. So I think this will be probably the first and the last time you will see a coupled carbon NMR. Most of them will be decoupled. Okay. So we have another example of a carbon NMR spectrum here. Okay. Carbons that are not attached to hydrogen give very small signals, meaning quaternary carbons. We've talked about primary, secondary, and tertiary carbons, right? The primary carbon will have 3 hydrogens connected to it. The secondary carbon, 2 hydrogens. A tertiary carbon, 1 hydrogen. Now what about a quaternary carbon? How many hydrogens do we expect? 0. Okay, that's an example of a quaternary carbon. So if I blow up this structure here, carbon label C is an example of a quaternary carbon because we have 0 hydrogens connected to it. Okay, and in the carbon NMR, it's easy to distinguish those quaternary carbons because they are the ones that will give you very tiny peak. They will always have a very small peak, and that's why we refer to them as a quaternary carbon here. This guy is here. You see that very small peak there? Is for proton C. That small peak represents proton C. So all quaternary carbons will always have very small signals in their carbon NMR. Does that make sense? Question. Are we good? Carbon NMR. Yes.
Why is CC and DD?
Why C and D? That's a good question. That's a good question. Remember that carbon itself is electronegative. It also depends on the number of carbons you are connected to. Okay, it depends on the number of carbons you are connected to in this case. So if you look at C is connected to 1, 2, 3, 4 carbons, whereas D is connected to 2 carbons. That's a good question. Good one. I don't know. I don't know. I will figure it out. Okay. Yes, because logically you probably want to expect C to come before B. I will let you know in the future. Are we good with carbon NMR? Now, in the carbon NMR, there's a special type of NMR called the depth. Okay? It's called depth. It's a special type of carbon NMR. It's a special type of carbon NMR. And the depth NMR is good because it can help us distinguish between CH, CH2, and CH3 carbons. Does that make sense? We can distinguish between the CH, CH2, and CH3 carbons. Okay? Now, in a typical carbon NMR for this citronella or whatsoever, citronella, it's an aldehyde. In a typical carbon NMR of this compound, that's what the typical carbon NMR of the compound will be. This is a normal carbon NMR of that compound. Okay? That's the normal carbon NMR. And so it tells you the number of signal tells you the number of carbons you have in the system. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. So in this system we have 9 different types of carbon. So this and this is 1. Okay? 1, 2, 3. That's my niece. It's happened here. Yeah, it's getting old. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Does that make sense? So the number of signal tells you the number of carbon. And again here, this is a carbon double bonded oxygen. I will most likely say this signal here corresponds to that carbon double bond oxygen. Does that make sense? And if you look at here, you have these 2 carbons here. These 2 carbons here, because they are sp2 carbons, you remember what we said on that table, they should appear somewhere here. So this signal here will represent those sp2 carbons. Does that make sense? Okay. Now look at them. You have this one, upper one. Let's call this the upper one and the lower one. Which is which? Which is which? You have the upper and the lower. The taller one, which one does the taller one represent? Between the signal. The taller one will represent the upper. Because remember, the lower one, how many hydrogen does it have? 0. And remember, we said when you have 0 hydrogen, your signal is short. Does that make sense? So over here, because the signal is short, I will most likely say it represent that carbon over there. Does that make sense? And so that's how you can go ahead and use the carbon NMR and match it to the structure. Now, the depth. My phone is ringing again. Now, with the depth, you can distinguish between the CH3, the CH2, and the CH. Does that make sense? Now, if you carry out depth, you can make in such a way that the depth can only show you the presence of the CH carbon. Only the carbon that bears 1 hydrogen can be shown in that NMR experiment. Yes. So you can fine-tune the instrument to give you only the carbons that bears 1 hydrogen. You can do that and ask the instrument to give you only the carbons with the CH2 or the carbons with the CH3. Now, there is another type of depth which is called depth 135. It's not shown here. And that's the one we'll be talking mostly in this class, and we'll do more example in the lab. The depth 135, instead of producing 3 different signals, will produce 1 signal. So you will have 1 spectrum in the depth 135. And then you have 2 types of carbon, what we call the even carbons and the odd carbons. The even carbons will have an even number of hydrogens. For example, CH2 is referred to an even carbon. And the odd carbons will have an odd number of hydrogens. For example, the CH3 and the CH. Those are odd hydrogens. In the depth 135, the even carbons will appear below the spectrum. So if you look at the depth 135, you will see some signal pointing downward. And the signal pointing downward are for the even number of carbon, meaning CH2. Then the signal pointing upward, you have some signals on the depth 135 that are pointing upward. Those signals are either CH3 or CH. That's the one I think you guys should remember, because that's the one we'll be using most often. Does that make sense, guys? Depth 135. The CH2 appear below the signal line, whereas the CH3 and the CHs appears above the signal line. Does that make sense? That's all about carbon NMR. Now don't be carbon NMR. Correlation spectroscopy, proton correlation spectroscopy, COSY. Let's talk about it, COSY. It's a two-dimensional NMR. Two-dimensional NMR. Okay? This, in the COSY, we will have two proton NMRs. In a COSY spectrum, you have two protons NMR. There are two proton NMR. One is displayed on the x-axis. The other one is displayed on the y-axis. They are all proton NMRs. Okay? And so when you display them together, you have some signals that define a certain diagonal here. Those signals are represented with dots. Okay? And the dots that lies on the diagonal represent protons that couple with each other, with itself. The dot of the diagonal represents protons that couple with itself. Okay? So if I see this first dot here, that represents proton A. It simply means that my proton A couples with proton A. Does that make sense? And so that doesn't give you useful information. It means you couple with yourself. Now, there are other signals that are off diagonal, meaning they don't lie on this diagonal here. You can see this signal, this, or that one, and that one. And usually, the diagonal defines a symmetry. What is in the upper half of the diagonal is exactly what is in the lower half of the diagonal. So you only choose one half of the diagonal to interpret. Does that make sense? Whatever is here is also down there. And so we are only focusing on one half of the diagonal. So in this COSY spectrum, if we look at the signal here, this signal here, that signal simply tells us that proton A, because the line goes towards proton A, is coupled to proton B. It simply means that proton A is standing next to proton B. That's what the COSY tells you. Does that make sense? That's the meaning of being coupled, meaning you are standing next to, you are adjacent to. Is that okay? If we look at this signal, signal Y, if I look at signal Y, you need a nice ruler, okay? If you draw a straight line, where does it go? Where does it go? Does it go to this one? It's this one, right? Yeah. So that is C. Okay, Y goes to C and Y also goes to E. Does that make sense? It means that proton E is standing next to proton C. Does that make sense? That's the way you interpret your COSY. And you can see it. Proton E and proton C, they are next to each other. Is that okay? If you look at signal Z says proton Z is standing next to E. And that is D and that is E. They are standing next to each other. That's what the COSY does. The COSY gives you information. The COSY gives you information about adjacent protons, the ones that are next to each other. Yes, sir. Oh, yes, ma'am. Sorry.
The last one you said, did you say proton D and proton E?
Yes, D and E.
So how are those next to each other?
Which one?
D and E.
This one and this one? 1, 2, 3 bonds away.
Oh, okay.
So you have the COSI and then the rest. The last type of NMR we'll talk on Thursday will be the head call. That's the last type. Okay? And then on Thursday we'll spend more time solving problems. You know, I'll come up with some NMR, I will post them on Blackboard, and I expect you guys to do them before you come to class, okay? At least go through them. Because if you don't go through them and actually just sit here and watch me doing it, it will be like me, you know, it will be like me speaking Homala. Yes. So make sure you do those problems before you come to class. Attempt them. Look at them. So that we can only answer what you didn't understand. Does that make sense?